am Ekaterina Filimoshina, and firstly, I want to thank the organizers for the opportunity to give this talk. Today, I'm going to present my joint work with Dmitry Shirokov on some Lie groups in degenerate geometric algebras. In this work, we introduce and study several Lie groups in degenerate geometric algebras, or Clifford algebras. These Lie groups preserve the even and odd subspaces under the adjoint representation and the twisted adjoint representation. The considered groups can be interesting for the study of spin groups and their generalizations in the degenerate case. This presentation consists of the four main parts. First, we will provide some necessary notation and give the well-known facts on the degenerate geometric algebra GPQR and the Jacobson radical. Then, we are going to consider the adjoint and twisted adjoint representations. Afterwards, we will introduce the four types of Lie groups in degenerate geometric algebras: P plus minus, P plus minus lambda, and P lambda. We are going to give the definitions, provide some examples, and show the relation between these four types of Lie groups and the groups preserving the even and odd subspaces under the adjoint and twisted adjoint representations. And then we will consider the Lie algebras of these four types of Lie groups and make some conclusions. Degenerate geometric algebras, in particular plane-based geometric algebras or PGA, which were actively discussed yesterday, have various applications in computer graphics and vision, motion capture, ray tracing, etc. Moreover, the degenerate algebra PGA can be realized as a subalgebra of conformal geometric algebra CGA, which was discussed yesterday too. So we hope that the results of this work can be interesting for various applications in computer science. Now let us provide some necessary notation. Let us consider the geometric algebra or the Clifford algebra GPQR over a vector space V. We consider both the real and complex vector spaces. We use F to denote the field of real numbers in the case of the real vector space and the field of complex numbers in the case of the complex vector space. The identity element is denoted by E. The generators are denoted by EA. In the real case, they satisfy these conditions, where eta is the diagonal matrix with P times 1, Q times minus 1, and R times 0 on the diagonal. In the complex case, the generators satisfy these conditions too, but with eta with P plus Q times 1 and R times 0 on the diagonal. We use lambda with the lower index R to denote the subalgebra GOOR of the algebra GPQR. This subalgebra is the Grassmann algebra. It is also called the exterior algebra. We denote the subspace of the fixed grade K by GPQR with the upper index K. This subspace consists of the linear combinations of such elements with ordered multi-indices of length K. The subspace G0 is denoted without lower indices PQR, since it does not depend on the signature of the algebra. The grade involute is denoted with the hat. This operation determines the even and odd subspaces. Their elements are linear combinations of the elements of even and odd grades, respectively. Now, let us consider the Jacobson radical. The Jacobson radical is the set of the elements of such form. Any degenerate algebra GPQR contains the structure of the Jacobson radical. In our work, we use the Jacobson radical and its properties to prove the main statements. Now, let us consider this arbitrary element of the Jacobson radical in detail. First, let us consider EA, EB, and EC, where A, B, and C are ordered multi-indices with a non-zero length. Note that the square of each of the green generators in EA equals +1. The square of each of the red generators in EB equals -1. And the square of these generators, the yellow ones, equals 0. Then an arbitrary element x of the Jacobson radical has the following form. where VC, VAC, VBC, and VABC are in the field F. Note that each of the summands in X contains EC, the yellow one. It means that each of the summands in X contains at least one generator which square equals to 0. So the Jacobson radical consists of such multivectors. In the particular case of the Grassmann algebra GOON or lambda n, we obtain that the Jacobson radical is the direct sum of the subspaces of all grades except 0 grade. In the particular case of the non-degenerate geometric algebra GPQO, the Jacobson radical consists only of 0. Now let us consider the center of the degenerate geometric algebra. It is denoted by ZPQR. It is well known that the center of GPQR has this form. We also need the subset SPQR of the center ZPQR. This subset has this form. We denote the subset of all invertible elements of any set this way. For example, the group of all invertible elements of the center is denoted like that. In our work, we consider the 4 types of groups preserving the even and odd subspaces under the adjoint and twisted adjoint representations. We denote the adjoint representation by add, and the twisted adjoint representation by add with the check mark. They act on the group of all invertible elements in the following way, where U is a multivector. The kernels of the adjoint and twisted adjoint representations are the following sets. These sets consist of all invertible multivectors T, preserving any multivector U, under the adjoint and the twisted adjoint representations, respectively. It's not difficult to prove the following lemma. The kernel of the adjoint representation coincides with the set of all invertible elements of the center, this one. And the kernel of the twisted adjoint representation coincides with the set of all invertible even elements of the Grassmann subalgebra of the algebra GPQR. So now let us introduce the 4 types of Lie groups P, P plus minus, P plus minus lambda, and P lambda. The lower indices PQR in the notation of these groups shows the signature of the algebra in which the group is considered. Here you can see the center ZPQR and its subset SPQR as a reminder. The first group is the group P with the upper index plus minus, the yellow one. Note that the upper index plus minus means that we consider the even and odd elements. This group is the smallest one and it has the simplest definition. So this group consists of the even and odd invertible elements. The second group is the red one, P without any upper index. This group is defined as the product of the group P plus minus and the set of the invertible elements of the center of the degenerate algebra GPQR. Also, we prove that there is the second equivalent definition of the group P, where there is the subset S instead of Z. The third new group is the blue one, P with the upper indices plus minus lambda. The group P plus minus lambda is defined as the product of the first group P plus minus and lambda. In other words, it is defined as the product of the first yellow group and the set of all invertible multivectors of the Grassmann subalgebra lambda R of the degenerate algebra GPQR. And the fourth group is the purple one, P with the upper index lambda. We define this group as the product of the group P, the red one, and lambda. In other words, it is the product of the red group and the set of all invertible multivectors of the Grassmann subalgebra lambda R. Moreover, this purple group can be defined in the other ways, using the blue group P plus minus lambda or the yellow group P plus minus. You can see these equivalent definitions of this group on the slide. So we introduced these 4 types of Lie groups. At the top of the slide, you can see the main definitions of the 4 introduced types of Lie groups as a reminder. Now, let us consider these groups in the two main special cases. In the case of the non-degenerate geometric algebra GPQO, and in the case of the Grassmann algebra GOON, or lambda n. In the case of the non-degenerate algebra, these four groups coincide if n is even. If n is odd, we have two different groups, blue and yellow, and purple and red. Note that in the non-degenerate algebra, the two groups with the upper index plus minus, blue and yellow, coincide. And this group is considered in the paper, in this paper. And similarly, the two groups without the upper index plus minus, purple and red, coincide too. And this group is considered in this paper. And in this work, we generalize the results of these two papers. Let us consider the Grassmann algebra GOON, or lambda n. We have two different groups if n equals 1 or n is even. And we have three different groups in the other cases. Note that the yellow group always coincides with the set of all invertible even elements. The blue and purple groups always coincide with the set of all invertible multivectors of the Grassmann algebra. Now, let us give some examples on the four introduced types of Lie groups P in the cases of the low-dimensional degenerate geometric algebras. We use that the degenerate geometric algebra can be embedded into the non-degenerate geometric algebra of large dimension, which is isomorphic to the matrix algebra. In the first example, we consider the Grassmann algebra GOO1. This degenerate algebra can be embedded into the non-degenerate algebra G110 using the well-known Clifford-Jordan-Wigner representation. For example, it is considered in this paper. This non-degenerate algebra G110 is isomorphic to the algebra of the 2x2 matrices over the field F, which can be real or complex. So we have the following matrices for the identity element and the generator E1 of the degenerate algebra GOO1. We obtain that the group P plus minus is isomorphic to the group of all invertible elements of the field F. The other three groups are isomorphic to this set of the matrices, where x0 and x1 are in F. In the second example, we have the Grassmann algebra GOO2. This degenerate geometric algebra can be embedded into the non-degenerate algebra G220 using Clifford-Jordan-Wigner representation. And this non-degenerate algebra G220 is isomorphic to this matrix algebra. We get that two of the groups which have the upper index lambda are isomorphic to the following matrix group. The other two groups without the upper index lambda are isomorphic to this matrix group. Note that in the second example, we obtain the subgroups of the lower triangular matrices group, which is closely related to the Heisenberg group. So these groups may be useful, for example, in quantum computing. In theorems 1 and 2, we give several equivalent definitions of the four introduced types of groups: P, P plus minus, P lambda, and P plus minus lambda. And these are the equivalent definitions. Note that we have already discussed the first definition of each of the groups on the previous slides. This one, this, and this one. Also note that in the other definitions, we use the Jacobson radical here, and the Grassmann algebra. We use some of these definitions to prove the further statements on these groups and on these types of groups. So we have introduced the four types of Lie groups P. At the top of the slide, you can see the definitions as a reminder. Now we want to show the relation between these four types of groups and the groups preserving the even and odd subspaces under the adjoint and twisted adjoint representations. We use this notation for the groups preserving the even or odd subspace under the adjoint representation. And this notation for the groups preserving the even or odd subspace under the twisted adjoint representation. If k equals 0, it means that the group gamma preserves the even subspace. That is the subspace of all even elements. And if k equals 1, the group gamma preserves the odd subspace. Note that these groups gamma are the analogs of the well-known Lipschitz group, which preserves the grade 1 under the twisted adjoint representation. The spin group is the subgroup of the Lipschitz group. And our 4 types of Lie groups can be interpreted as some kind of analogs of the Lipschitz group. The following theorem is one of the main results of this talk. In theorem 3, we prove that the 4 introduced types of groups preserve the even and odd subspaces under the adjoint and twisted adjoint representations respectively. Namely, the groups P and P lambda preserve the odd and even subspaces respectively under the adjoint representation. And the groups P plus minus and P plus minus lambda preserve the even and odd subspaces under the twisted adjoint representation. Note that in the special case of the non-degenerate algebra GPQO, using theorem 3 and the definitions of the 4 groups P, we obtain that all the groups gamma coincide if n is even. And there are 2 different groups gamma if n is odd. In the particular case of the Grassmann algebra GOON, we get that there are 3 different groups gamma. It is interesting that gamma 0, that is the group of all invertible elements preserving the even subspace under the adjoint representation, coincides with the group gamma 1 with the check mark, which is the group of all invertible elements preserving the odd subspace under the twisted adjoint representation. We have introduced the 4 types of Lie groups P. There are the definitions. Now, let us consider the Lie algebras of these Lie groups. We denote the 4 Lie algebras of the corresponding Lie groups in the following way. On this slide, the Lie algebras are colored in the same way as the corresponding Lie groups: yellow, red, blue, and purple. In theorem 4, we prove that these 4 Lie algebras are as follows. And moreover, we calculate the dimension of each Lie algebra. Now, let us make some conclusions. In this work, we introduce the 4 types of Lie groups: P plus minus, P plus minus lambda, and P lambda. We consider both the real and complex degenerate geometric algebras of arbitrary dimension and signature. We prove that there are several equivalent definitions of these types of groups. We also prove that these types of groups preserve the even and odd subspaces under the adjoint and twisted adjoint representations. Moreover, we studied the Lie algebras of these Lie groups. These 4 types of groups are interesting for consideration since they are closely related to the degenerate spin groups. In the extended version of the paper, we are going to consider the other groups, preserving the other fundamental subspaces in degenerate geometric algebras under the adjoint and twisted adjoint representations. Namely, we are going to consider the subspaces determined by the grade involution and reversion and the subspaces of fixed grades. Note that the well-known Lipschitz group preserves the subspace of the fixed grade, the first grade, under the twisted adjoint representation. We are going to consider the analog of the Lipschitz group in the degenerate geometric algebras. Then we are going to normalize this Lipschitz group analog and obtain the analogs of the spin groups in the degenerate case. And these analogs of spin groups can be used in applications. And that's all. Thank you for your attention.